Hello everyone, and welcome to the final lecture for the third week of the Introduction to Data Science module. So we're going to be getting into more depth with Pandas. We introduced Pandas in the previous lecture as a powerful package for working with tabular data, data that's easily expressed or represented in a table format. It's based upon NumPy arrays, so it's very efficient in computing aggregate statistics. And as we'll see, Pandas is very expressive in its syntax for slicing up data frames, transforming them, and applying various transformative or aggregating functions. So we'll import pandas as PD as usual, and as I just noted in the previous lectures, we introduced the kind of star of pandas, which is the pandas DataFrame. That's the sort of table object that we make use of in Pandas. And we covered how to construct these data frames both from data in memory, like lists or dictionaries, as well as reading and writing to disk. And we also looked at some of the basic data manipulation methods for retrieving, removing, or adding data. We're going to do some examples of working with both numerical and categorical data from the popular online review site Yelp to explore some of the kind of computational and data wrangling capabilities of Pandas. So on your machines you should have a compressed JSON file called yelp.json.gz. It's a couple megabytes, and we've got some code here that'll go ahead and load that into a data frame for you. The gist, if you look at it, we open the gzip file with the gzip module. We read in the file line by line and construct kind of this list and dictionary data structure typical of JSON by using json.loads on each individual line. And then for constructing the data frame from that's fairly straightforward. If we look at Yelp data, we look at the first three entries, we see there's a dictionary corresponding with different businesses reviewed on Yelp, and there's all these different kind of keys for each business. So there's attributes, and that actually contains nested set of dictionaries, business ID, categories, city, and all of these fields become the various columns of the data frame. So this is somewhere between the examples we saw in the previous lecture when we were reading JSON files into a data frame, where it's reasonably representable as a table. Each row corresponds with a business. Many of the columns have primitive data types, but there's also certain columns that contain data structures. Categories has lists, hours and attributes both contain dictionaries, generally speaking. One thing I may not have mentioned in the previous lectures, but I should have and will again when we discuss SQL, which is also oriented towards working with tabular data. There's kind of like a scheme or idea or blueprint for how a table should be set up. People have thought very hard about this, and but the general gist is that each row corresponds with some kind of singular or atomic idea, object, event, or record. So things like a business or a person, a user of a product, a particular moment in time. These sorts of things usually correspond with the rows. A soccer match. So those are some like objects and events. You might have records of sales or bank transactions, all sorts of things that are sort of like nouns, things we think of as nouns, basically. And then the columns represent the characteristics, attributes of that object. So each business has, well, some attributes. A business ID, categories that it belongs to, a city, an address, hours, more geography, a name. These are all kind of the characteristics we would use to describe one of these objects. So the columns tend to be more like adjectives in a way. And each column, each attribute, should be a single type of measurement, more or less. Name. And here we have all the same sorts of things, you know, words. Longitude or latitude, same sorts of things, like numbers, degrees latitude, degrees longitude. Star ratings, numbers 0 through 5, which means that the columns are typically type homogeneous. They have one kind of data, while the rows are type heterogeneous, because the objects are described by a variety of heterogeneous characteristics. So that's just a brief discussion of how to think about tables, generally speaking. We'll be bumping up against this idea a few more times throughout the course. And maybe we'll describe in more depth why it's advantageous to approach tables in this way. But for now, I'm just going to highlight that that's the way we think about tables and move on. So, so that's written out right here. And since the columns are generally type homogeneous, data frames have a dtypes attribute that illustrates the dtype, or data type, which is familiar from NumPy, of each column. So many of these things are type object because they are either data structures or strings. Strings get type object because essentially a string could be any particular length. So it's unknown kind of how much memory it might take up in advance. So in the discussion from NumPy, we learned that the efficiencies of NumPy came from knowing that all your objects in the array are going to be the same size. That was one of the sources of NumPy's efficient computation. Since strings can be different lengths, they can take up different space in memory, so we can't really make them all uniform. So strings in Pandas are data type object, but these fields, these columns that have numbers are floating point. Review count is integer because we have integer counts, and open is a bool, so true or false. So variety of data types here. Object is going to be inefficient. It's going to be slower for doing computations, and it's going to take up a lot more space in memory. If we can avoid data type objects, it's best to do that. So for example, imagine we had a column here with date times, say maybe the date and time that it registered with Yelp, so that it was added to Yelp. You could represent that as a string, which would make it data type object. But there are also date time objects. Let's see. So here we have a Python datetime object. These are uniform in size and are useful for a great number of things that I'm not going to get into right now. We'll get into it later. But this is also a valid data type within Pandas. So for instance, if we had a bunch of date times represented by strings, one way to make our data frame more efficient would be to turn those strings, or parse those strings, into datetime objects. And if you look through the Pandas documentation, you'll find there's many methods and places where you can do that. As mentioned in the previous lecture, we can reference columns by name. So the data frame is a dictionary of objects. And I'm going to introduce a new term now, which is the proper name for the columns. And columns are properly called series, data series, or Pandas series. So a data frame is a dictionary of data series. And we see these are, Pandas objects. The series is essentially like the constituent part of the data frame. Data frames are built from series. They're a dictionary of series. At their core. I mean, there's more going on than that, but at their core they are a dictionary of series. And a series at its core is a NumPy array where the positions are labeled with an index. So a series has an index which labels the rows. In this case, our index for this data frame is just an enumeration of the rows, 0 through however long the data frame is, 37,938. So in this case, the index is not any different from the position of the rows, but in principle, it easily could be. For instance, we could set the business ID to be the dictionary, the index, and we would be able to uniquely reference maybe, I mean, I assume the business IDs are unique, but if they're not, then this isn't true. But assuming the business IDs are unique, then we could uniquely reference excuse me, each row by business ID, which is useful if we know those in advance. If we don't, then it's not so useful. So, given that a data frame is a dictionary of series, and a series has these labels for the rows in the index, the series is also kind of dictionary-like. The index is essentially a set of keys for referencing the rows. So we can also access individual elements of the table by using sort of a compound dictionary slicing syntax. So we can first slice out the city series and then slice out row 100 from the index, which turns out to have the value Madison. Now, on the other hand, since a data frame is a dictionary of series, we can't do this in reverse order. This will be interpreted as the name of a column, but there is no column named 100, so we get a key error. 100 is not in the dictionary of series. There is no series called 100. So this is a case where we would have to use the lock method if we wanted to access kind of things in this order, although functionally it's going to be the exact same as that up there. Lock is generally, I would say, unless you're slicing out a whole column, lock tends to be the preferred method of accessing specific rows. Lock is the preferred method for accessing specific rows. So I've been emphasizing the fact that the data frame is a dictionary of series because you will often encounter errors like key errors, and remembering that a data frame is a dictionary of series will help you interpret these kinds of error messages or avoid errors altogether. So one of the major uses of, or like powers of the data frame that I've mentioned several times is data frames have really nice methods for slicing up the data and performing aggregations. So we've already seen a little bit of the data aggregation methods in Pandas. We took a mean of a data frame. There's also a describe column, which will show us a collection of summary statistics for various columns. So these are all the numerical columns, and describe calculates these summary statistics, which give a nice view of kind of the distribution and characteristics of the numerical quantities in the table. But we will usually want to do some kind of more complex analysis than just calculating these simple summary statistics. So we'll be making use of a handful of methods over and over again in Pandas, namely group by for slicing up the data into groups, and then apply or aggregate for transforming and aggregating the data according to groups or in its entirety. And once again, there is a terrific write-up not only of how to technically do this in Pandas, but how to think about these sorts of operations. So once again, I want to give a shout out to the Pandas documentation. It's exceedingly good, and I highly recommend if you are feeling confused about any of the topics we discuss in this notebook, or when you get to using Pandas in the DW mini project. That's DW, not PW. I definitely recommend that you revisit this section of the Pandas documentation and have a look through it. You don't need to read the entire thing, but it's definitely a helpful kind of alternative to what I will show you. So, just by way of review, we'll make a little example data frame. So, since a data frame is a dictive series, one of the most natural ways to construct a data frame is to use a dictionary of series-like objects. So here, series-like just means essentially something like a list, or a tuple, or a NumPy array, some linear data structure. So I've got some usernames here. I'm going to generate some random passwords from the ASCII character set and digits 0 through 9. And I'll also generate some random creation dates for these accounts. And then we saw this before. My preferred method for constructing a data frame is to have a dictionary where we have the names of the columns and then the data structure containing the values. So here's our data frame. We have our 3 users created at different times with some passwords. And you can see I used this datetime object to make the creation dates. So took today's date and subtracted a random number of days from between 0 and 1500 days, roughly 4 years ago or so. And if we look at df.dtypes, oh, all 3 are object. Interesting. I would have expected this one to be a date time. Let's see if I can't pass in a keyword argument. No, that didn't work. datetime creation dates. Okay. I'm not really sure why that was required. I think it should have worked anyway. But nonetheless, I used the Pandas toDateTime method for to coerce Pandas into interpreting these creation dates as date times. And so now we see the datetime 64 data type here. And there's no outward visible change in the representation of data, but the internal representation has changed from presumably a string to, well, I don't think presumably a string. It should have been datetime objects, but now to one at least that Pandas understands and is happy to work with. I'm going to move through this rather quickly since this is quite a few things we've seen before. If we want to create a new row, we can simply use dictionary-like assignments, slicing into, if we want to add a new column. So we slice into the name of the new column and give the values to assign. And if we want to make a new row, we do that using lock. And of course we can also drop these as we saw in the previous notebook. So much the same as what we saw in the previous notebook, but with a different set of examples. So if you want a refresher, you can have a look through those on your own. Here we're constructing a data frame in a slightly different way, where we pass in usernames as the index rather than as a column. So here username became a column in the data frame because it was one of the entries in our dictionary that we use to construct the data frame. Down here we're making it we're setting the index to be the usernames. And it can also be useful to give that index a name. So we set the index's name attribute. The data frame has an index attribute. That index has a name attribute. So here we see that index's name. And now, if we wanted to pull out particular users, we could do that by username. One element here that we haven't seen before is set index. So as we will see, the index is functional. It controls how data is treated when we are working with multiple data frames or multiple series. For instance, if we are combining series, they get combined based on their overlap in index. So two elements with the same index are put into correspondence. So it can be often useful to change what the index of a data frame is from time to time as we want to do different manipulations on it, especially in combination with other series or data frames. So there is a set index method that lets you take any column and set that column to be the index. So if we first construct this data frame and set the names of the columns, we can turn this username column into the index by using set index username. Just like drop, this is by default not a mutation. We have to explicitly indicate we want it to be a mutation with in place equals true. Otherwise, it will return a copy. So now df has username as the index, and we can easily reverse this process by resetting the index. So reset index will move the index to a column and generate a new index that is simply an enumeration of the rows of the table. It's also possible to have an index with multiple levels. So here we have a multi-index. In principle, maybe there would be multiple usernames associated with a single email, or multiple emails associated with a single username. And a multi-index allows for that kind of structure. It's not super common to make use of multi-indexes, but some data sets kind of necessitate it. Or certain operations on a data set may put you in the situation of having a multi-index. So they do come up. We've worked through reading CSVs, so I'm going to skip over this section. But again, just another example if you need more study on how to read in data into Pandas, there's more material for you here. So in particular, there's an example of setting the index from the data. So that username as index. Additionally, an example that has no header. So here we have our data, but with no header attached to it. And we have to provide the names of the columns. And also a tab delimited example. So here the data is not delimited by commas, by tabs. We use a different delimiter. So this is the escape character for a tab. So A and B separated by a tab, \T. Okay, so on to some new stuff. Often we won't want to pick out particular entries in our data frame that we know in advance. Instead of, I might not be looking for a particular business in my Yelp data frame. I might instead want all the businesses in Arizona, or all the businesses that have more than 3 stars, or less than 10 reviews. So often I want to select or slice my data frame based on some kind of condition. And fortunately, Pandas makes this very easy for us. Or rather, NumPy makes this very easy, and Pandas inherits that feature from NumPy. So if we're only interested in businesses in Arizona, we can take the Yelp data frame and ask, where is state equal to AZ? And we can see this returns a Pandas series. So this is a Pandas series. Pandas series that where all the values are booleans, true or false. And what we can do is we can use this series, this Boolean series, to slice the data frame itself. So here I've put the Boolean series that we had earlier inside of Yelp DF brackets. So we're kind of using a slicing syntax around this Boolean series. And now if we look at the data frame that's returned here, we see state is always AZ in every entry. And additionally, we see there is a big jump in the index from 0 to 297 because businesses 1, 2, 3, 4 up through 296 were not in Arizona. So they're omitted from the result here. Note this is not a mutation, this is an operation. So I can still do Yelp DF head, and I'll see all my Wisconsin businesses are still in the data frame. I simply filtered the data frame by a Boolean series. And as I mentioned, this is functionality that's inherited from NumPy. So if I have an array, I can ask where is this array greater than 3, and that will give me an array of Boolean values. So I can say foo equals this array, foo greater than 3. Foo greater than 3 gives me an array of Boolean values, and I can use that array of Boolean values to slice foo. And so I get back foo where foo is greater than 3, and that's just 4 and 5. It's the exact same idea here with Pandas. This functionality comes from NumPy. It's inherited by Pandas. And it really shines in Pandas because we can build up these nice, easy to read conditional statements for filtering our data because of the labels of the column names and the descriptive names we give to the data sets. So we might store the result of that filtering, slicing out just the Arizona businesses, in AZ Yelp data frame. And if we use the unique method of a Pandas series to ask what the unique values of the series are, we see only Arizona in the result. So the unique values in the state column of Arizona Yelp DF is simply Arizona. And we can, like I said, build up, kind of complicated but easy to understand filters by combining different conditional statements. So if if I want the businesses in Arizona, where state is Arizona, and the review count is greater than 10, I simply say Yelp df state equals Arizona, and Yelp df review count greater than 10. Notice here we use ampersand. So if I have x equals 8, y equals 10, x greater than 5, and y greater than 9, or 8, normally for this kind of a statement I would use the word and. In Pandas, we use ampersand. This is called a logical and. This is called a bitwise and. I'm not going to get into the difference. You're simply going to have to remember that in Pandas we use ampersand. We also use pipes for or. So this is the character. If you do shift backslash, it's a vertical bar called a pipe. And instead of the word not, we use this tilde. So we'll look at some more examples of that. So with these two filters combined, we again see businesses in Arizona, but now we only see ones with review counts higher than 10. Previously, we had this Eric Goldberg, MD, who had a review count of 7. We also had Viad Tower Restaurants with 5 reviews. And in this filtered data frame, where we require review count to be higher than 10, both of those are missing. You see we have no more 0, and the 297 goes direct to 299. 298, which was that Viad Tower Restaurants, has disappeared. So this is just explaining how it works. Once again, we have a Boolean series, and as we saw from the NumPy example, that such a Boolean series can be used as a sort of index or slicing mechanism for the data frame. So if we have our little toy example data frame, we could ask for true, false, true. So that would give us Alice and Eve, but not Bob Smith, because that middle entry is false. So true, Alice, false, Bob, true, Eve. So we get Alice and Eve, but no Bob. And again, this is really useful because the filters become so easy to read. Yelp DF review count greater than 10. Give me the rows of Yelp DF where Yelp DF review count is greater than 10. Very straightforward. Now note, these don't necessarily have to be the same. I don't have to use Yelp DF review count values to filter Yelp DF. I could use this to filter some other Pandas object. However, the series must match. What happens is, the index must match. So the index of this series is used for evaluating, what in the thing we're filtering should be included or not. So it goes to each, it goes through the index of this series, looking true, false, 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 true, and gives you the entries with the index where the value is true in the data frame you are filtering. So, for example, if I had a data frame and I take out column A, and I say, give me column A where it's greater than 4, I can, since the index is 0, 1, 2, which matches the index on DF, I can use this to filter DF, because their index overlaps. So the Boolean values in this series the index of those Boolean values is used for matching up which rows in the thing I'm filtering are included or excluded. Another thing is to consider is that sometimes we will already have a Boolean series. So the Yelp DF open column has data type bool. These are a bunch of true and false values in this column. So we can just use that column directly if we want. We don't have to write a condition at all. We're already dealing with Boolean values. So if we want the open businesses, we just ask for where Yelp DF open is true. And if we want the closed businesses, we just negate the open column. Where open is true, the businesses are open. Where open is false, the businesses are closed. So if we want to retain the closed businesses, we have to turn all the falses into trues and all the trues into falses. So we negate that open column. And this gives us the closed businesses where open is false. And we negate it by having this tilde, which is equivalent to a logical not. Not open. Closed. There's also a very useful collection of string operations in Pandas, which can be used to do pattern matching. So another very good section of the Pandas documentation. Splitting and replacing strings, concatenation, not all that interesting, extracting substrings, testing for strings that match or contain a pattern. So this is kind of what we're interested in. So, for example, there's a lot of businesses in our data set in Las Vegas, but there's also businesses in Las Vegas East and South Las Vegas, and we might want to get all of them so we make sure we don't miss things that are basically in Las Vegas but have been had some kind of been labeled by their particular neighborhood rather than the whole city. So we'll ask for where in Yelp DF, where the city, so this gives us access to the string methods, this .str, contains Vegas. And again, if we look at this string operation returns a Boolean series. So we see some trues and a lot of falses. And if we use that Boolean series to filter the Yelp DF object, then we end up with these businesses that are all in Las Vegas. And we can see they're not all just Las Vegas. If we ask for the unique cities in the Vegas Yelp DF, where we assigned the result of this filtering, we see Las Vegas, North Las Vegas, Lake Las Vegas, South Las Vegas, and we also see a lot of things that motivate why this is kind of useful. We also got Las Vegas space, and there's North Las Vegas, N Las Vegas, and N dot Las Vegas. So this is a fairly common problem in data sets with strings, where when the data is entered, it won't necessarily be entered consistently. There are typos. There are disagreements about conventions of how specific information should be represented. Are your users' names or customers' names entered first name, last name then first name? So this kind of pattern matching can be very useful in those cases. I can tell you, for instance, during the application processes for this course, quite a few of you did not write out the same email address or the same name, whether due to typos or because you decided to put your first name first originally and then first name last later on. And finding out who's who involves exactly these kinds of operations. So how are we doing for time here? We've got about 6 or 7 more minutes. The next sections I think are very important, and I don't want to start them and then sort of stop. However, there is couple more things maybe that I can talk about very quickly in the little bit of time we have left, and then I'll come back and do some of the more serious topics in the lectures for next week. So a couple of brief topics. So I mentioned that for the most part we will treat a data frame as we would treat a dictionary. Mostly, we want to be working with the data based on names, not based on position. However, especially when it comes time to represent some result of our analysis, or as an intermediate stage or step in some kind of analysis, it can be useful to sort our data frame according to some set of values. So sorting is done by using either sort values or sort index, which do pretty much exactly what they sound like. It sorts the rows of a data frame either by the values in some particular column. So if we sort by stars, we see the lowest rated businesses first, and then it will ascend to the highest rated businesses towards the end. So if we turn this into tail, we see all the highest rated businesses. Or we can set a column to the index, or if a column is already set to be the index and we want to sort by that index, we use sort index. So here we set business ID to the index, and when we sort by index, we get this kind of alphabetical sorting of all the business IDs, all of the businesses by their ID. So apparently dash dash comes earliest alphabetically, and we see next we have like 1, 4, 5, capital B, capital D. So these are ascending through the alphabet. So that's sorting. Just like most operations in Pandas, this is not a mutation. This returns a copy of the data frame. This is an operation that returns a result. It is not a mutation unless we explicitly use the in-place keyword. And the last thing I'll mention is Pandas plugs in very nicely to some visualization packages. I might spend more time on this in the future. I'm not certain I will because it's not explicitly scheduled anywhere in the curriculum, but if I find time, I might do so. Pandas basically has a hook into matplotlib within the package, so we can very easily call matplotlib methods like plot and hist from data frames and data series. So if we have want to make a histogram of the logarithm of the review counts, we can just chain the .hist method onto our series. So here we have kind of our matplotlib visualization of the log review counts for every business. There's also .plot, pop growth not defined, cool. There we go. So you can, of course, use matplotlib explicitly and just use the Pandas series as linear data structures as you normally would when you are working with matplotlib and giving it NumPy arrays or lists of values. But you are also for exploratory visualization of data that you already have in a data frame, it can be very useful, or convenient at least, to use these methods that plug into matplotlib in the background and call them directly from Pandas data structures. There's a lot of customization that's possible in these calls. You can include keyword parameters, quite a lot of keyword parameters. which I am not going to really explore because there are so many of them. There's a link here to the documentation that shows just a few. This is not all of them. Here at the end, there is ** keywords, which refers to options to pass to matplotlib plotting method. So in addition to the ones shown here, there's also all the usual matplotlib keyword arguments that are possible in, say, plt.plot, which is just a huge variety of keywords. Harkening back to the lecture on matplotlib, visualization is infinitely customizable. There's kind of like an infinite number of visual solutions you could imagine, and accordingly, the code, unfortunately, therefore has a very large variety of options to explore when you're making visualizations. So that's going to wrap it up for this first in-depth lecture on pandas. Next week we will be getting into applying transformations and aggregating functions, as well as the group by method and joining data sets together.